Hello. In this part of the course, we're going to be going over the fun world of properties of relations. Okay, a relation, remember, is any two-place predicate is going to count as a relation, right? So anytime you have a predicate that has two individuals in it, you're saying something about how those two things are related in whatever way, right? And so there are many kinds of relations, an infinite number of them, really. And so we're going to talk about some properties that some relations have that are important to keep in mind when analyzing certain kinds of arguments and other sorts of things in language P. So let's talk a little bit about relations. Relations are predicates that relate two or more constants to one another. That is any two-place predicate. Different relations have different properties, okay? And we have to track those if we're to handle them logically. And the properties of relations that we will look at are all properties of what are called dyadic relations, that is two-place relations. There are plenty of multi-adic relations, but again, for our purposes, we don't have to worry about that. This is level 1 logic, not not level 80 or whatever. So first off, let's take a look at the property of relations that is symmetry. Okay, and so some relations are symmetric and some are not. Okay, what it means for a relation to be symmetric is that it holds in one direction, right? If it holds in one direction, then it will hold in the opposite direction, and vice versa, right? So that's what makes a relation symmetric, okay? And so consider these different types of possible relations, right? And so if you're saying x is equal to y, you're talking about a relation that x and y have, right? If x is married to y, it's a different relation that they might have. If x loves y, that's a different relation that x and y have. Or if x contains more riboflavin than y, then it'll be one thing or another, right? That actually brings me back to when I was a kid and my brother and I had sit at the table with our cereal and start reading the size of it. Mine has this much riboflavin. How much does yours have, right? I mean, like, a conversation that 10-year-olds make, right? It's what it is. Okay, so, but again, consider all of these different relations. And it's pretty clear when you look at these, and actually, if you've paused the video at this point and looked at those things that said, those, maybe I don't understand what symmetric is because it doesn't seem like those are all symmetric. Give yourself one super mega logic point, right? Like keep it in a notebook somewhere, super mega logic point or something like that, right? Or whatever, right? Because you're correct, they are not all symmetric relations, right? Obviously, x is equal to y is symmetric because notice the definition, right? If it holds in one direction, it holds in the opposite. If x is equal to y, then it has to be the case that y is equal to x, and that is what makes those symmetric. Okay, so likewise, if x is married to y, then y is married to x. Okay, also symmetric. Okay, but unfortunately, for many, right, and although fortunately for soap opera writers and really any writer of anything, the fact that x loves y is not symmetric, right? Just because x loves y does not mean that y loves x, okay? And so that's what we will refer to as a non-symmetric relation, okay? And again, if x contains more riboflavin than y, then it's impossible for y to contain more riboflavin than x. Okay, so that's a special different thing. It's not just that it's not symmetric, it's asymmetric, right? Okay, so there's the difference between asymmetric and non-symmetric can seem sort of crazy, but look, if you can't have a distinction of that kind in logic, you can't have it anywhere. So here we are. An asymmetrical relation is one that that if it holds in one direction, it can't hold in the opposite direction. So another example would be x is east of y. If x is east of y, then y cannot be east of x. Okay, so it's asymmetric, right? A non-symmetric relation is one that simply doesn't necessarily hold in both directions, even if it holds in one direction. Okay, and so an example of that would be something like x thinks y is pretty. Okay, right? So just because x thinks y is pretty doesn't mean that y thinks x is pretty, but y might think x is pretty. Okay, and so again, it's just non-symmetric, right? Instead of asymmetric or symmetric. And so now that you are comfortable with symmetry, asymmetry, and non-symmetry, now consider anti-symmetry. Okay, this is a weird one. The anti-symmetric relation, it's kind of a special case. I'm not really sure why it's called what it is. The name anti-symmetry doesn't really suggest this in the way that asymmetry or non-symmetry or symmetry are suggested in the other examples, but here we go. A relation is anti-symmetric when it is symmetric only when the individuals that are related are identical. Okay, so go over that definition a couple of times. Say it to yourself, get it clear in your head. Think of maybe a fresh example of it. One example is, for example, the relation x is less than or equal to y. Notice it's symmetric only when x and y are equal or identical in this case, when x is y, in other words, right? And so x is less than y is not symmetric, okay, or because y, can't be less than x if x is less than y. So that would be, so blank is less than blank is in fact an asymmetric relation. Okay, but if you say less than or equal to, now it's an antisymmetric relation. It's symmetrical only when x and y are the same. Right, and so that's a bit of a goofy case, but there it is. And so if you want the formal representations of these things, which is really the upshot of all this, here's what they look like. Okay, for symmetry, you have for all of x and for all of y. If x bears the A relation to y, then or x bears the A relation to y if and only if y bears the A relation to x. Okay, and so that means that again, that's a way of putting it that if the relation goes in one direction, x related to y, then it goes the other direction, y related to x, and vice versa. If y is related to x in a certain way, then x is related to y in a certain way for any symmetrical relation. So any relation that is symmetrical can be stated that way, where the A is the relation itself, right, the predicate. An asymmetric relation is one where if x bears that relation to y, then for all of x and y, then it is not the case that y bears that relation to x. Okay, so if x is greater than y, y cannot be greater than x, right? That's an asymmetric relation. And then, of course, then there's the antisymmetric relation. And that one says that they're symmetrical, but it says that if they're symmetrical, then they're identical. Okay, that's effectively what that says. For any two things, if they're symmetrical, it's only because they're identical. Okay, and that's the antisymmetric relation. And then, of course, there's non-symmetry. Now, I say here that non-symmetry doesn't really, and of course, non-antisymmetry and non-asymmetry don't really require formal representation. If you, for some reason, ever find a case in which that's not true and they do require formal representation and you're just not really sure you're doing it right, you can check the text because those are in the text. But in general, we're only going to need these when something is positively the case that it is a relation of a certain kind. If it's just not a relation of that kind, we kind of don't care enough to have to represent that formally. But it is in the book, right? Because the book is supposed to be more thorough even than any special case you might run into. And so let's talk then now about the transitive relation. It's another very common relation that we talk about. You've probably heard at least some of these things in mathematics, right? Because these are occasionally important in mathematics. So for example, a relation is transitive if it transits, right, sort of across a middle term. So consider the relation blank equals blank, right? And so if you have an argument like if w equals x and x equals y, then w equals y. So notice the equals transits from w to y across x. Okay, that's one way of sort of putting that, and that helps to remind you, oh, that's what transitive means. It transits that way. So any property that does work in that kind of an argument is transitive. Any property that doesn't work in that kind of an argument is not transitive or non-transitive. Okay, and so consider the relations x is taller than y, right? So if x is taller than y, right, and y is taller than z, right, then x is taller than z. Okay, seems like that works. That should be transitive. And lo and behold, it is. But now say, well, x talked to y and y talked to z. Does that mean that x talked to z? Well, not necessarily. I mean, x might have talked to z, but they didn't have to. So again, it's simply not transitive, right? And if you want to say if x is a parent of y and y is a parent of z, well, then x cannot be a parent of z, right? They would have to be the grandparent. That's although I'm actually thinking of a case in which that actually is possible. And so this would simply be not transitive. But again, assuming all laws are followed, okay, we're going to say that if x is a parent of y, then x and y is a parent of z, then x cannot be a parent of z, right? So that would be intransitive, okay? And we'll see other examples of this as we go. And so here are formal representations of transitive or intransitive. The transitive one, again, if you look at it, just says, look, if x bears the a relation to y for all of x and y, and y bears the a relation to z, then x will bear the a relation to z as well, right? So that's how you explain, right, in language P that that a, the predicate there, is in fact transitive. If a as a predicate here, and again I'll mark on this one, a is the predicate, right? If that's intransitive, right, then it will be the case for all x, y, and z that if x bears the a relation to y, and y bears the a relation to z, then it will not be the case that x will bear the a relation to z. Okay? All right, so, and then of course, again, non-transitivity generally doesn't require any special formal representation, but if you want one, you can see some examples of that in the text. All right, so now let's talk about reflexivity. Okay, what it means for a relation to be reflexive is if it holds between any object and itself, right? So reflexive, right? So that's the Latin root actually makes a whole lot of sense. But think, sort of reflex, so turn it around and come back, right? So reflect, your mirror reflects your image. So think of it in that sense, reflective almost rather than reflexive, even it's a very similar root. So what it means for a relation, again, to be reflexive is it holds between any object and itself. Okay, so consider, again, the equal relation. So if blank is equal to blank, then it's, so look, if x is equal to y, well, then y is equal to x, okay? Notice that's symmetry, right? Easy to get mixed up with reflexivity. Reflexivity is going to be if x, is going to be whether x is equal to x, right? Again, if it's reflexive, then x will be equal to x, and it seems like that has to be the case. X has to be equal to x, doesn't it? And so, yes, it does. And so that means that that's a reflexive relation. Okay. Now, can one be married to oneself? Okay. Again, generally, no. I mean, again, there may be some legal jurisdiction in which this is the case, but in general, no, you can't be married to yourself. It takes two to tango, so to speak. And so, if the idea is that you cannot have x married to x, then it's not reflexive, right? It's in fact, it's one of those things. It can't be the case, and so that's irreflexive. Okay. And then if you look at a relation like loves, so you want to say, okay, does x love x? Well, maybe, maybe not. Right? That's different than saying, is x equal to x? Definitely. Is x married to x? Definitely not. Does x love x? Maybe, maybe not. Okay, that just means it's non-reflexive. It's also non-irreflexive. Okay, and so again, formal representations of those are as follows. Reflexivity is for all of x, x bears the a relation to x. Okay, that's how you say that a is reflexive. The way that you say a is irreflexive, you say for all of x, x does not bear the a relation to x. Okay, and then if it's just not reflexive, again, we don't have to have a formal representation for that. And if it's not irreflexive as well, but again, they're in the book if you want them. And so again, keep in mind that relations can have one, right, or more than one, or even all of these relations in some combination. Within some limitations. So for example, an example of a transitive property is something like is heavier than or is taller than. Okay, a symmetric relation would be one is like is not equal to. Okay, if x is not equal to y, then y is not equal to x, right? That's symmetric. Reflexive is that sort of x knows what y is thinking, right? So again, now it would be really x knows what x and y have to be the same thing, right? And so we're going to say for any x that equals y, x would have to know what x is thinking, thus x would have to know, y would have to know what y is thinking, etc. So again, reflexive. We're putting x and y instead of blanks in there, but something has to be reflexive if some object bears that relation to itself, right? And of course, you could have something that very sadly has none of those properties, right? Loves, right? If x loves y, right, that's not transitive, it's not symmetric, and it's not reflexive, right? So it's in some sense the saddest relation, and yet again, so fortunate for writers of all kinds. But of course, you can have various relations that are many of these things. Okay, so you can have relations that are transitive, symmetric, and reflexive. In fact, identity is one famous property we're going to talk a lot more about, that as a logical property anyway, is transitive, is symmetric, and is reflexive. Okay, also being in the same place as, being the same age as, right? You know, in some sense, subsets of identity have all these properties. You could say that relation blank has met blank, right, is both symmetric and reflexive. Okay, that, you know, the idea is that you certainly people have met themselves, right? You couldn't not have met themselves, and you know, if X has met Y, then Y has met X, right? You could have relations that are both transitive and reflexive, but not symmetric, right? You can have relations that are transitive and symmetric, but not reflexive, right? And so, etc. Like, you can have combinations of these or not, and it's just, you know, you take it relation by relation. Say, what properties does this one have? What properties does it lack? And there you go. And so here's some other things that are just sort of interesting logical necessities. And if you really want to give yourself a bunch of super mega logic points, like in your little notebook, write it down. You should like pace through these and figure out why. Why does it have to be the case that, say, for example, all asymmetric relations are irreflexive? Okay, and like think of a few examples of each, and I think you'll probably see why that has to be the case. Or that all irreflexive and transitive relations are asymmetric. Okay, and why all intransitive relations are irreflexive. There are actually proofs of these things, right? Which if you knew how to do proofs in predicate logic, you could prove these things, but we're not going to make you do that. Okay, so here's why it matters. So our system of formalizing does not encode information about what kinds of relations there are, right? It simply says that it's a relation. Okay, so if you have some predicate letter with, you know, an X and a Y in it, or an A and a B in it, or a V and a W, or whatever, right? You're saying there's a relation between V and W, and the relation that is specified by the predicate, but you're not really specifying exactly what relation that is. You're just sort of symbolizing it. And so because we're taking all the content out of language when we put it into our logical language, we're leaving only the structure. And so you might think, oh, well, gosh, all these properties of relations, they must be properties of the, you know, the content. It's like, well, sort of yes and sort of no. It's the content that always tips us off as to what kinds of relations that, you know, are different, what kinds of properties different relations have. But you can represent it as just a matter of structure. That's why all of these properties of these relations, they do have formal representations. And so lots of times in some arguments, information of that kind is just left unstated when we state the argument in English. But that information is required if we're going to state the argument in P. Okay? And so an argument, there's a special word here for this. It's a fun word. It's a great word. Use this word to impress your friends. Any argument that leaves out some essential premise, something that it has to have in order to be valid, but oftentimes we just leave unstated, that's called an enthymeme, right? An enthymeme is an argument that's stated in an incomplete way, right? In a way that's like, okay, look, you know, so for example, if you say, you should not smoke because smoking is bad for you, that sounds like a complete argument, but it isn't really. It's an enthymeme, right? Really what you mean is, you should not do things that are bad for you, and smoking is bad for you, therefore you should not smoke. So it's that you shouldn't do things that are bad for you that we just left unstated, right? So again, enthymemes, right? They're arguments that where a little bit of it is left out because it seems like it goes without saying, or people tend to pick it up clear enough in context. Well, we don't have any context in P, and so we're going to have to supply some of that in another way. Right, and so again, an enthymeme, right, is an argument that leaves at least one of its premises unstated, usually because the premise goes without saying. And so for an example of this, consider the argument Al is taller than Bob, Bob is taller than Claire, therefore Al is taller than Claire. Okay? It's as clearly valid as anything is, there's some content in what it means for one thing to be taller than another that lets us get that this is a valid argument. But once we put it in P, I think you'll see that there's some problems. So here is what it looks like in P. You have Al is taller than Bob, right? We have Bob is taller than Claire, right? And then Al is taller than Claire, right? That's, pretty straightforward. Here's the tree for that entailment relation, for that argument. And it'll be one of the easiest trees you ever do. That's what it looks like, right? You put out the set and then you negate the thing that's supposed to be entailed. And if it opens, it's invalid. And so Invalid, right? Didn't we just say that was as clearly valid as anything? So again, there's something going wrong here, something we have to fix. All right, so again, this is an enthymeme, okay? So in English, the meaning of the phrase is taller than made very clear what kind of relation it is. But in P, again, we're preserving the structure only, so we have to add a premise. We have to say, okay, we're going to say, TAB, or TAB, TBC, TAC, right? And this T thing, the T is a transitive relation. We have to add that to the argument. And so we have to add this information that X is taller than Y as a transitive relation. And so in P, again, we'll use the formal representation of transitive relation, but we'll put T in there because that's the one that's transitive, in this case, the is taller than relation. And that's how you say that is taller than is transitive. You say, look, for every X, Y, and Z, if X bears the T relation to Y and Y bears the T relation to Z, then X will bear the T relation to Z, right? And that'll actually get us where we're going. So in fact, this is the tree then for that. Again, you start out by putting your premises on the tree, right? So A is taller than B, right? B is taller than C. And the crucial missing premise that was missing from the tree before, and it'll make all the difference for all of X, for all of Y, and for all of Z, if X bears the T relation to Y and Y bears the T relation to Z, then X will bear the T relation to Z. Okay? In other words, T, whatever it is transitive. And then what we do is we negate the thing that's supposed to be entailed here just to see if it'll close. And if it closes, the entailment relation holds, and if it doesn't close, then it doesn't. Okay. Now remember how to do trees with quantifiers on them. We're going to have to in fact, we're going to have to deal with this line here because it's the only one that has any connectives or operators on it at all. And notice the main connective or operator is this quantifier here, right? It's going to be tempting to try and deal with all of them at once. You can't do that, right? You can only deal with the main connective of anything, whether you're doing a proof, whether you're doing a tree, whether you're doing a table. That's never been anything but the case. And so the idea is that this thing, right, if you remember your rules for universals, should be decomposed, right, should be instantiated for every constant on the table. And so you want to say, for A, for B, and for C, because those are the constants that are on the table. Now, you can use a little bit of judgment and know that you're going to get this a little faster. If you, okay, look, you're like, this is the thing we're interested in representing. This is the thing we're represented in representing, right? And we're interested in getting this one where we need to get it. So again, you can use a little bit of judgment and really just sort of instantiate these things once. And once stuff closes, of course, you don't have to put anything into a closed branch. It's closed. And if they're all closed, the tree's closed, right? Even if there could theoretically be more work to do. Okay, it closes, it closes. And so the idea is that once you decompose, once you instantiate this universal for all of X and for all of Y and for all of Z, Tx, Y, Tz, all this stuff, right? Once you instantiate that, you get this, okay? You get for all of Y and for all of Z, if A bears the T relation to Y and Y bears the T relation to Z, then A bears the T relation to Z. So we've put an A in place of the X in the earlier sentence. Now we have a new universal, right? We have this one here that is the and again, if you know your rules for universals, you say, okay, we're not theoretically done until we have instantiated it for A and for B and for C. Okay, but again, you can use a little judgment and say, let's just instantiate this for B next. Okay, and then we're going to get this phrase here. Okay, and so the idea is that we now have for all of Z, if A is taller than B, right, and B is taller than Z, then A is taller than Z. Okay, great. And so we know that in order to get the thing we want to get, we're just going to have to instantiate this one here. And so again, this is the main connective of this phrase here, the main operator, I should say. And so now, again, we should have to instantiate this for A, for B, and for C. But again, if we just start with C, we know that we're going to get somewhere we want to go with this. So just use a little judgment. And so again, instantiating this universal for C replaces all the Z's with C's, right? It's got to be careful saying that one, especially over the phone or whatever. And we get this sentence here, okay? So if this one says then, if A is taller than B and B is taller than C, right? Because we substituted that there, then A is taller than C, right? Great. That's just the outcome of T taller than being transitive, and it being true that A is taller than B, and true that B is taller than C. Okay. Now we have the main connective here. We have is the conditional there, And so that will branch as usual. So remember, conditional is true only when either, so either its antecedent is false. Okay, that's this part here. And so we're going to put that down there, make it false. Or its consequent is true. And so we're going to take this consequent, we're going to put it down here, right? And now notice immediately that this branch here is going to close, okay, because we have TAC and not TAC on the same branch, okay? So there we go. And so that leaves us only with this sentence here to decompose, and it is a negated conditional, okay? That means not both. If we mean not both, we mean either not one or not the other, okay? And so we're going to put those on branches. This one will close because we have not TAB and TAB here on the same branch, okay? And then this one will close because we have TBC and not TBC on the same branch. Okay, and so if everything closes, you're done, right? Even though technically, right, you could very well instantiate this thing, 2 more times, and this thing 2 more times, and this thing 2 more times, and just make a really long tree where everything's still going to close, right? So I actually sort of thought to myself, I wonder if I plug this into a computer, if the computer will just brute force it. Right, and we'll just give you some kind of a tree that's gonna like just gonna be hugely long and everything, where everything still closes, but everything gets instantiated all the times, followed to make sure all that stuff. But actually, I plugged it into a computer, and it shouldn't be any surprise that computers can do this just fine, because that's all that computers do is logic. We'll actually cover that exact topic later in this course, not very much later. It's coming soon. But plugging it into a computer. This is actually what you get. You get a tree that uses the exact same judgment that a reasonable human would use here. And it's like, well, of course, if it can be programmed to do the tree, it can be programmed to do the tree in the most elegant and space-saving way possible. So, yeah, even a computer's not going to do it the ridiculous way. So, so there you go. You just want to learn how to use a little judgment on these things. And if a computer can do it, you can do it, because the computer can't actually think at all. And actually, interestingly enough, if this was in my old set of notes, and so I just left it here, if you want to know how to do this in a proof, here it is, right? It's actually quite an easy proof. Notice we haven't really covered any proofs in P, but you'll notice they don't work that much differently than proofs in S. You just have to add some stuff for how to handle universals, and actually it's how to handle existentials that's fairly hard in proofs, but again, you don't have to worry about that. But if you were curious, here it is.